Thanks for that, Scott, and thank you to everyone who is able to join me today for this technical briefing on 802.11n. This is actually the second episode in our series of 802.11n Essentials and Applications webinars. In this session, we will look more closely at the recommended best practices for network design and site surveying. Today's topics will include a look at the new wireless expectations, how 802.11n signaling travels further and faster, suggested best practices for designing for distance and for speed, an in-depth look at channel usage, especially with 40 megahertz channels for 802.11n, and a summary of best practices exemplified today. Let's begin with the new wireless expectation. The landscape for networking has changed. Part of the reason it's changed is because of the influence of wireless LANs. But in addition to that, the entire business model has changed, and what people do and expect from their networks in general has changed. The applications that run on the networks has changed, the equipment used to access the networks has changed, and the user experience and expectation levels has also risen. And with that comes an expectation that the networks will be able to support mission-critical applications, and with wireless extensions to those networks, it's expected that people should be able to have access pretty much from anywhere at any time to these resources. In order to do that, the network engineers and designers need to take into account the different requirements for the different services and applications that run on the network. And these services and applications can all have different requirements and different specifications. In order to get all of these different applications to work together and play nicely on the network can take a little bit of design and finagling to make this all work together. Fortunately, we have some new resources to help us with that. And the biggest one of the bunch is the new amendment to the 802.11 2007 standard known as 802.11n, which was brought to us by Task Group N of the 802.11 Working Group. 802.11n, which was ratified in September of 2009, and includes over 500 pages of specifications, allows us to use orthogonal frequency division multiplexing in the 2.4 or 5 gigahertz band, so it works in either one of the bands. It's referred to as high throughput, and most of the discussions around 802.11n have to do with the higher speeds as high as 300 megabits per second today, with 450 and possibly 600 megabits per second coming in the near future. So that's what gets most of the attention. There are many other features built into 802.11n. Some of them we'll see right away. Some of them may not be delivered to the market and be available off the shelf for many months or even years into the future, if ever. Here are some of the main improvements to the 802.11n amendment to the specification that are available. Many of these are available now, some of them in the near future. In our first segment of this discussion, the first webinar, we took a high-level look at all of these, touched on all of these. And today I would like to spend a little more time discussing two main improvements, the ones probably that have the biggest effect on your network from a design and site serving perspective, and that is some of the changes that have to do with traveling further, which is in the column labeled robust performance, and the amendment changes that allow us to have higher throughput, and that's in the columns on the left. The biggest ones here that we're going to have time to discuss today have to do with receive diversity and spatial multiplexing, also the use of 40 megahertz channels. So let's take a closer look at that. To understand how to engineer your network for more robust performance, in other words, how can we deliver higher speeds at further distances, we should first take a look at how site surveying and network design has been done in the past for wireless LANs. So first of all, legacy receiver sensitivity thresholds, the numbers that you see on the chart in front of you, are the key to designing the edges of your cells, or basic service areas as they're called in 802.11 terminology. So the cells that you see, or that we talk about, the coverage ranges inside an 802.11 network, have to do with how strong a signal is being generated from the radios. Now the radios can either be the access points or the client devices, or in many cases we have to consider both. So normally when we do a site survey or a network design, we talk about where to place access points and how far out from the center of the access point, how far radius we expect the signal strength to reach. And when we do the designs on paper, we calculate roughly where we think these coverage areas will extend to. Then we go out and verify that with a site survey. And when we perform the site survey, what we're looking for is these numbers that you see in the columns to the right half of this chart. So the numbers that are labeled either data or voice are the numbers that we're looking for. There's really two ways that you can perform the site survey based on these numbers. One is if you're using receive sensitivity threshold levels or receive signal levels, or if you want to be a little more accurate, you can use signal to noise ratio numbers, and both of those sets of numbers are on the chart here for you. These are pretty standard numbers. They already have some amount of margin built in to allow for shadowed areas and unexpected performance of wireless in your network. And what they mean is this: if you look down the chart, you see the numbers on the right, but you also over to the left see something called multiplexing methods, and to the right of that you see modulation levels, and then you see data rates. And it's usually the data rates that everybody focuses on. So if you're trying to build a network with let's say 802.11b technology, and you wanted to make sure that you had 11 megabit per second coverage everywhere, then what you would have done in the past was to engineer your network for a neg 72 dBm signal strength at the cell edges, and by performing or by allowing inserting enough access points into your network, making sure that there's enough coverage so that when the cell areas overlap, and we're talking about different channels here, as the cell areas overlap on different channels, the signal strength is negative 72 dBm or stronger, then you would have engineered your network and verified it through the site survey for an 11 megabit per second connection. For a number of years now, we've had quite a bit higher signaling speeds thanks to 802.11a and 802.11g than what we previously could get with 802.11b. And those are the speeds that you see on the multiplexing methods that are labeled OFDM. So 802.11g and 802.11a both use OFDM and can have much higher signaling rates, up to 54 megabits per second. So if you wanted to engineer your network for 54 megabits per second, either 802.11a or 802.11g, notice the difference that you would have to accommodate in your network when you did the design and site survey. Instead of a neg 72 dBm signal strength, you would have to accommodate a negative 61 dBm. Now remember that since these are negative numbers, the closer you go towards zero, the stronger the signal is, and the further away from zero you go, the weaker the signal would be. So in other words, neg 61 dBm is much stronger than neg 72 dBm. And in order to make that happen, you're going to have most likely more access points in your environment in order to make sure that you have that much energy out there. Okay, so how do you do that? Well, it all starts on paper and you start calculating out your areas, but the easiest way to do that is by using a predictive site survey or propagation modeling application. And there's several good ones on the market. There's several vendors who have site survey software that will allow you to model the environment before you actually go out and place the access points. Okay, but the focus here today is on designing and doing the site survey. So keep this in mind. These numbers are very important. These are previously what we would have used to design and verify our network. Now let's take a look at a connection. This is a screenshot from one of our laptops here in the lab, and I've got this. It's an 802.11n capable client device. It's a laptop, and it's currently connected to an AeroHive access point. It says it has a 65 megabit per second connection. If you noticed on the last chart, there was no 65 megabit per second signaling rate there, and that's because 802.11n has many more signaling rates aside from the ones that you saw previously. So with 802.11n, we get a whole big new chart to deal with. In this case, this connection, when we've connected to the access point and we hover our mouse over the Microsoft Wireless Zero Configuration wireless icon down here, this little pop-up balloon says we've got a signal strength that's excellent and a speed of 65 megabits per second. So in order to understand what that 65 megabits per second really refers to, let's go to this next slide and take a look at the 802.11n modulation and coding schemes chart. So here's another chart. Look at all the numbers and all the different possibilities. And this is by no means all of the possibilities. The first version of 802.11n actually has over twice this many MCS indexes. The ones that I've shown here are the most likely to be seen in the near future and the ones that we want to concentrate on for our site surveys. So the way that we get all these different numbers, all these different signaling rates, is through combinations of many of the features built into 802.11n. And what those new features are and how they would be used and how they would affect your network is really kind of an in-depth thing that we need a little more time to discuss. But just know that through combinations of the new coding rate, multiple spatial streams, whether you're using single wide or double wide channels, whether you've enabled short guard intervals, all of these things together, these combinations allow you to get all these different signaling rates. Now that chart is kind of small. Let me make it a little larger and show you that I've made a version here that is actually active. So because there's so many different possibilities here, it's hard for me to understand and focus on what could be happening. For instance, if you look at the chart a few minutes ago, if you were to look at the, let's say the 802.11g rates, you would see that it's based on modulation levels, and the bottom type of modulation is something called binary phase shift keying. If I click on this modulation coding scheme index 0, BPSK with half rate coding, if I click on that, I see that there are actually 4 ways to use BPSK with half rate coding within the first 32 modulation coding scheme indexes of 802.11n. And the biggest thing that changes is not the modulation level, but the number of spatial streams. And the number of spatial streams, we'll talk a little bit more about this in just a few minutes, but quickly, spatial streams have to do with the number of independent transmissions that are going on simultaneously, either the same amount of data, the exact same data, or non-redundant data that can be occurring from the multiple antennas contained within an 802.11n radio system. So we can have 1, 2, 3, or 4 spatial streams currently. We also could be using a 20 megahertz channel or a 40 megahertz channel. We could be using either a short guard interval or no short guard interval. The default would be no short guard interval. Now, if we were to take a look at all these different levels, you can see it can get real confusing as to what's being done at what time. So, for instance, if we were to take the connection that we did a screenshot from on the previous slide that showed a 65 megabit per second connection, and if we start trying to look through this chart to figure out you know, how's that being accomplished? 65 megabits per second. I've located one here, and I see that this 65 megabits per second is MCS index number 7, which uses 64 QAM with 5/6 coding rate. Okay, but I wonder if there's any other ways to arrive at that. Well, with this chart, I can just click on any 65 megabits per second, and it will show me all the possible ways that you can roll a 65 megabit per second in the first 32 MCS index levels of 802.11n. And we see that there are basically 3 ways. Now, if you happen to know that your equipment will support 3 spatial streams, then perhaps this is the way that you've arrived at that. So with QPSK 3/4 rate coding and 3 spatial streams, you can hit 65 megabits per second. But if you happen to know your equipment does not do 3 spatial streams on the access point and or client, then it's more likely to be one of these two, either MCS index 6 or 7, that's accomplishing that. So you might be wondering, yeah, well, what's the big difference and why would you care? Good question. Let's take a look at the next chart and slide to try to answer that. Okay, so here is pretty much the same chart. I've tried to simplify it a little bit. I've only shown the first 16 MCS index levels, and I want to focus now on what we've added to this. So we have all the information from the last chart, and in addition to that, I've gone down into the standard and pulled out the received signal strength levels and the signal to noise ratios, and also have included the recommended fade margins that are recommended by the 802.11 working group, and have added that all in. And you can see here, for instance, that BPSK half rate with a single spatial stream requires on a 20 megahertz channel a neg 70 dBm signal. If you were to try to accomplish BPSK half rate coding on a 40 megahertz channel, well, you need twice as strong a signal, a neg 67 dBm signal, to do that. Okay, now you should know that these numbers that I've put here for you are calculated for a 10% packet error rate, which is okay for data and even for high speed data. So you can trust these numbers if you are trying to engineer and design a network for data only. However, if you're trying to use real-time applications, voice and video, you may not trust that number. You might want to bump up that fade margin a little bit, add another 5 dB or so to it. That would be a good working number once you did that. But more likely, when you get the applications, if you're using SpectraLink phones, Vocera voice badges, something like that, your vendor will have already calculated and already have a recommended receive sensitivity threshold or signal to noise ratio that you should try to follow. And I'd suggest that you use their numbers if you have those suggestions to work with. Okay, now let me take a look at the active version of this chart. A little bigger, a little closer and easier to see. And just want to point out, for instance, let's go back to our neg 65 megabits per second. If you remember, or 65 megabits per second, remember that in the first 16 MCS index levels, there you could get a 65 megabit per second by using either MCS index 6 or 7. And there's very slight difference here. So what is the big deal? Well, if we come over and take a quick look, and I'll just concentrate on 20 megahertz channels for now, we can see that mod index 6 requires a neg 53 dBm signal strength, while mod index number 7 requires a neg 52 dBm. So which one is easier to achieve? Well, the one further away from 0 is the one that's going to have the furthest reach out from the access point and from the client adapters. So if you have client devices that are not, you know, super strong transmitters, then you may probably be trying to engineer your network for neg 53 dBm. There's not much difference here. I agree that it's only 1 dB of difference, but right now I'm just trying to make a case and show a point of what would be the difference between these two and how does it affect your network designs and of course your site surveys. All right, There are many other ways to do this and many other numbers in here that you might be engineering your network for. But basically that's it. This is what we're looking for at the edge of our cells, where we come to the edge and we drop from one type of modulation level to the next. What is that number that you're looking for? And here it is on this chart for your convenience. Okay. Now, that mostly had to do with network design. Now let's go in general. Now let's take a closer look at designing for distance and how 802.11n actually allows our signaling to reach further than it could with previous versions of 802.11, even at the same output power levels, same antenna configurations and everything. We're going to see that 802.11n pushes out further than it did before. And here's why. Okay, because of the use of multiple input, multiple output systems, which is basically advanced antenna systems used in 802.11n, we have to have a different viewpoint of how the antennas are operating. I'm sure you've all seen 802.11n devices that have 3 or more antennas on them. And it's these additional antennas that help us improve the distances. And it's because the signaling can be used in a couple of different ways. So at its very most basic level, by sending out a signal, the same signal on 2 separate antennas, we can actually today receive those 2 separate what we call streams of data and add them together at the receiver side to have an improved, stronger signal. And what we're really doing is improving the signal to noise ratio. So we've improved the robustness by using more than one antenna to send the same signal out, and by using multiple antennas on the receiver to receive more of the signal and add it together intelligently, we're able to improve our signal against the background noise that is there. And by doing that, that allows us to use a higher modulation index level. Okay, so here's an animated version of that slide you saw just a second ago. It may help to clear some things up. So in this case, we've got a 802.11n 2-stream transmitter, the laptop, and the antenna on the left, antenna 1, is transmitting a stream of data. In this case, it is a different stream of data. It is what we'll call the blue stream, and it's transmitting data A. And on antenna 2, the antenna on the right, we've got the green stream, and it's transmitting a different stream. It's more information. It's not just redundant, but it's a separate data stream. So we've got 2 data streams of different data going out at the same time. It's being received at the access point that we see at the top of the screen, and the access point has 3 antennas. So at the receiver, antenna 1, the antenna on the left, is the primary antenna for receiving the blue data stream. Antenna 3, the antenna on the right, is the primary antenna for receiving the green stream. But the antenna in the middle is really used to recover signal and add it to both the other antennas. So the antenna in the middle is actually able to receive redundant data from both of those streams and use it to reinforce the signal that's being received on both antenna 1 and antenna 3. The result of that is the data from the blue stream is being received at a higher level, a higher signaling rate, receive sensitivity level, receive signal level, which allows us to use the higher or highest modulation levels for that particular modulation coding scheme index level. And the same is occurring on the green. So without going into too much more detail, just know that one antenna receives the primary signal, one antenna receives the other primary signal. The one in the middle is actually reinforcing both of the primary antennas. In order to prove this, we put this through a test, a field test. So we kind of like to prove and practice what we preach. And so before we put together, or while we were putting together this webinar, I was able to go out into the Wireless Training Solutions RF test field, which is right across the street from our facility. And it's a big test area. It is about 300 feet wide, 550 feet long. So it's almost the size of 4 football fields, and that makes it a pretty nice environment for testing Wi-Fi. And you might be surprised at what results you're going to see here. So here's what we used. We used the RF test field. I used this is the actual tough book running the latest, greatest version of Ekahau Site Survey Professional version 5.0. And this is a Panasonic tough book. Outdoor, it's field tough. It's tested for drop capabilities, and it's real nice for outdoor work, especially if it rains once in a while. It's moisture resistant. It also has an integrated legacy 802.11 ABG client adapter, and that's what I used to do the test. So we set up 2 access points. One was 802.11n, one was legacy 802.11ag, and set all of them out to signaling at the same time. And we went out with this tough book and performed the same test at the same time and compared the result. So for the legacy access point, we used a classical old school Cisco AP1231AG dual band. Everything is in autonomous mode, and we set this up with, on the 2.4 gigahertz radio, we set it to channel 6, set the power to 13 dBm, and used the the standard 2.15 dipole omnidirectional antennas, the rubber ducks that you see. Now, the integrated antenna that comes with this 802.11a radio is the paddle style antenna you see there, and that's an omnidirectional, slightly higher gain than the dipoles, and it was 3.5 dBi, so a little bit higher gain on that antenna. Set it on the 5 gigahertz channel, Uni 1, channel 36 at 13 dBm. Then we set up this 802.11n capable dual band AP1252 Cisco. Wanted to keep it all in the same family. Any other vendor's products would have had the same results. This was just what we happened to use for this test. And we set this also in autonomous mode. We set up the 2.4 gigahertz radio on channel 11 so as not to give any more interference than necessary to our legacy radio. Set the transmit power. Now we're using the GUI interface, so the closest I could get the power settings on the 2 access points, 13 dBm on the legacy AP, 14 dBm on this 802.11n. That's pretty close. It's within a dB, but we will need to take that into account with our calculations. And then I set up the 5 gigahertz radio on channel 48 and also output power of 14 dBm, and we were able to use dipoles on both of those radios. Then we set them up and set them at one end of the field, right here at outside the training facility, and then we went out and performed a pretty comprehensive site survey. Now you'll see you might have expected this, since it's a wide open field, that you would have expected to see kind of a smooth transition from one signal strength to the next, but Wi-Fi just doesn't work that way. Radio is always bouncing and reflecting, even off the ground, off of buildings many hundreds of feet away, and the signal is never just nice and smoothly attenuating. Instead, you see all these different areas, these pockets and islands of different speeds. How can you account for that? You can't predict it. You can really only measure it or use a propagation modeling tool. So here's what we saw, and try to take a look at this. And I know they look very similar, so it's kind of difficult maybe to see at first glance what the differences are there, but it is kind of noticeable. So on the top, we've got the heat map that was generated from our site survey for AP1. That's the legacy access point, and we're looking right now at the 5 gigahertz channels, and you can kind of see This reddish brown area accounts for, I'd say, I'm going to say about 50% of the entire heat map here. If you go down to the lower one, which is the 802.11n, then you can see that it's really the brown instead of the reddish brown accounts for more of it. And especially out at the edge, 550 feet, almost 2 football fields away, we still got a real strong signal here. It's a neg 65 dBm signal compared to the legacy access point, which was closer to neg 70 or maybe even weaker out here at the edge. So what accounts for that? And keep in mind that we had slightly different power levels. So let's take a look at that. We noticed that the legacy access point had a 13 dBm output, and the 802.11n had a 14 dBm. But also notice that the antenna on the 5 gigahertz legacy was more powerful, and it was about 1.5 dB more powerful. So make any comparisons you want, and you've still got about a half a dB more EIRP coming off of this top AP than you do off the lower one, and yet the 802.11n access point appears to have a stronger signal in this great big wide open free space area. It's even, I think, a little easier to see on the 2.4 gigahertz maps. Let's take a look at this one. And here we have once more on top the legacy AP, on the bottom the 802.11n AP, but now we're looking at 2.4 gigahertz. And there is a slight difference here of about a dB. So we have to remember that, because everything else is pretty much the same. The only thing that's different is the transmit power from the 11n access points at 14 dBm. It's about a dB higher than what we saw with the legacy AP. But if you notice the strength here, the signal in this field is weaker, even more weak than what we saw with the 5 gigahertz. And we see that a majority of the coverage is somewhere between neg 70 and neg 75 dBm. While when we look at the 802.11n access point signal coverage, it appears that the majority of coverage, or a good 50% of it, is in the neg 65 to 70 dBm. And that tells you right there that there is a good, almost somewhere between 3 and 5 dB of additional signal strength coverage, just for no other reason than we've gone to 802.11n. Everything else is the same, except for, if you prefer, you can remove another dB for the signal strength there. Other than that, 802.11n goes further. Okay, and is that a good thing? Well, sometimes, and sometimes not. It really depends on what your quality of service requirements are. When you're designing your network, sometimes you're trying to get the furthest coverage that you can get, the biggest cells possible. There's reasons to do that. For applications that have very stringent roaming requirements, you may want to make the cells very large, especially if you only have a few quality of service requiring users, so that they're not roaming very often. However, if you have to support lots and lots of users, then it's more likely that you'll want to keep your cells small, so that you can get lots of users who have a good, strong signal, good data throughput. If that's your requirements, then you want small cells. And in that case, going to 802.11n, all of a sudden your cells got bigger. If you had engineered them previously for 11a or 11g, and you just drop in your 11n access points, now maybe you don't have the same quality of service that you had before. Here's why. Now let's take a look at designing for speed. Okay, so back to our multiple in, multiple out diagrams that we had something similar a few slides ago. What's different here is that now we're using a 3x3 instead of a 2x3 system. And we'll be talking more now about spatial multiplexing. So previously we used 3 antennas to receive 2 spatial streams. Here we've actually got 3 antennas, both for transmitting and for receiving. The key to multiple in, multiple out, what's different about it from classical 802.11a and 802.11g is that the multiple access points in the classical legacy type of equipment, no matter how many antennas there was always only one radio, and the one radio would choose which antenna to use. It would always use only one antenna. But with multiple input, multiple output systems, such as we see with 802.11n today, the antennas actually have their own distinct radio. And even though all in this case 3 radios and 3 antennas may be transmitting, they may be transmitting different streams of different portions of the data stream, or they may be transmitting the same data over at the same time. If it did that, of course, then at the receiver you would have the same data but at a much stronger level. And if you were sending different portions of the data stream over the 3 independent spatial streams, you would get much higher throughput. You would expect to see, you know, somewhere around 3 times the amount of throughput that you would see normally. So here's an animation that kind of should help to describe that a little better. And what we've got is from the access point at the bottom of the screen, antenna 1 is on the left and it is sending the blue stream of data. Antenna 2 is in the center and it's sending the red data stream, and antenna 3 on the right is sending the green data stream. On the client laptop, which is at the top of the screen, the primary antenna for receiving the blue stream is on the left. Primary antenna dedicated to receiving the red stream is in the center, and the primary antenna that receives the green stream is on the right. So we have 3 independent data streams, and this can be 3 different portions of the user information that you're trying to transmit. So you can see by this you should be getting somewhere around 3 times the amount of throughput that you would have previously using legacy equipment. And it's all because we're using more antennas. But the key to this is it's the antennas that you can see. The part you don't see is inside the access point or inside the client device, and that's that each one of the antennas has its own radio. And if that radio can both transmit and receive, then you can have full spatial streams, independent spatial streams for each one of the antennas. Okay. So with all that said, and all the discussions of the speeds of 802.11n, no doubt you have heard of speeds that are just, you know, amazing speeds, 300 megabits per second, 450 megabits per second, and those are true. But what they are, those are the signaling rates. So signaling rates are when you transmit, when you have a transmission opportunity and you transmit a certain number of bytes of information, how fast do you transmit that? It's based on the modulation type that you're using, okay, and the number of coding streams and all the other little factors that apply. But what the actual throughput is something different, and usually that's what end users are thinking about. It's how many megabytes of information do I have to transmit, and how long is it going to take me to download this 100 megabyte file. That's usually what end users are focused on. When they run their mouse over the little wireless connection icon down in the system tray, and it says they've got a 300 megabit per second connection, but their signaling speed seems to be no faster than what they got with 802.11g, that's when, you know, that's when they can turn around to you and say, hey, what's wrong with this network? What did you do wrong? And it's those expectations that we need to set. So it's important to segment signaling speed. The physical layer transmission speed is not the same as the average throughput of user data over a period of time. And so what you should expect to see, and what I've seen here in the lab, what we've seen in the class workshops and exercises, is that current state of 802.11n, you can see anywhere from no better than what you had previously, 22 to 25 megabits per second, up to 100, I've even seen 150 megabits per second. But that's rare. more often I see speeds that go anywhere from 50 megabits per second to around 90 megabits per second, or close to 100. That's what I usually see. That's what I think that you'll probably see at least here at the beginning. The reason why is, well, there's several reasons. First of all, signaling speeds have to do, well, the signaling speeds are how much data we transmit during the speed that we transmit during a transmission opportunity. But don't forget, we're using half duplex radios. There is management and control traffic overhead that has to be transmitted, and it has to go over the same channel that your user data is going over. So when you're transmitting that, you're not transmitting user data. There's contention mechanisms, because this is a shared medium and everybody has to take turns on it. And the more people you have contending for the medium, the less often you will be the one transmitting your user data. Also, in order to make sure that the data was received correctly, whenever we transmit a data frame, we have to receive an acknowledgement before we can move on to the next frame. So until an acknowledgement is successfully received, that transmission could still be a failure. In addition to that, no matter how hard we try and how well we engineer our network, there are going to be collisions. And in 802.11, only one transmitter is allowed to be active within a channel, and I should say within a basic service area or a cell at a time. If two transmitters go active at the same time, that most likely will result in a collision. If they are close enough and strong enough of a signal to each other, they most likely will collide with each other, which means that there will be no acknowledgments for that frame for either of those users, which requires both of those transmitters to recontend for the medium and then retransmit that same information again. So again, that takes away from your overall throughput. So all of those things put together is why we see speeds that are usually no greater than about 50% of whatever the maximum signaling level would be. So with that number in mind, you might say, okay, I've got a 300 megabit per second connection. I should be seeing a good solid 150 megabits per second. Well, in a perfect world, that can be true. Like I said, I have seen 150 megabits per second, but that's rare. And anything, I think, over 120 to 150 megabits per second today is rare, not because the equipment, not because the access points can't do it, not because the firmware or anything can't keep up with it. It's more because of what the client devices are. So it really depends on what you're using for a client. We usually focus on the access points and say, okay, we've got an access point here. It's top of the line, greatest, best there is on the market. It's top dog, and it can do 3 spatial streams. That's great, but can your client do 3 spatial streams as well? Most likely not. I mean, it's possible, but not that likely today. So most 802.11 enterprise APs today can do at least 2 spatial streams, and many of them today can do 3. Okay, so with 2 spatial streams, we should be able to do 300 megabits per second. But the client adapters that you have may be anywhere from 1 to 3 streams. And how do you know that? Well, you need to do a little digging to find that out. Here's something else too. Client antennas are typically have less gain than the antennas on the access point. Keep that in mind, and remember that the client devices themselves probably have less power than your access points. So here is a best practice and a key tip for engineering your network. It's very important that you set the power level of the access points no higher than what your client devices can do. And that's probably right there going to go against all the logic you've used in the past. But think about it. Here you are setting up access points. Access points are plugged into the wall. They have continuous power. They've got you know, all different types of antennas that you can hook up to them. In many cases, they're able to go 40 milliwatts or higher, 100 milliwatts of power on the access point. But your client devices usually can't go that high, and they have these little integrated antennas normally. Okay, so the reason that you don't want to have an asymmetric power output between the access points and the client devices is because when you site survey your network and you're going out surveying and checking the signal strength from the access points, and it shows that you've got a good strong, let's say neg 61 dBm signal clear to one end of the building, you think that that should work for your clients, but your client devices are much weaker. And so yes, it's true that at one end of the building they can see the access point, but when they try to talk back to it, they don't have enough power, or the power that they do have drops them down into a much lower MCS index level. And so for that reason, you have asymmetrically engineered your network and verified it with a site survey that is only proving that the access points can reach that far. It's not proving that the client devices can reach back. So how do you manage that? Well, you can't really site survey for the client devices because they're moving around all the time. You never know where they're going to be. The best thing you can do is try to determine what types of client devices are going to be used in your network, and then set the access points so that they don't go any higher than that. Now, if you're a believer in automated radio management systems, and that's fine if you are, I have no problem with that. If you like to set the wireless LAN controllers and let them choose the channels sometimes and the output powers, that's fine, but try to set the wireless LAN controller maximum powers so that it goes no higher than what the client devices can do. For instance, if you have client devices that can only output 14 dBm of power, and that's calculated with the built-in antenna, then you should calculate the output power from your access points as being no higher than 14 dBm. So that's not just the output of the transmitter radio, but it's also the gain of the antennas of the access points should be no higher than 14 dBm in that particular case. So hope that's clear. If it's not, then I'm glad to talk about that through email. Just shoot me some emails and we can discuss that further. Okay, the client capabilities vary widely. So I just took a look at, I pulled a bunch of client devices we have here in the lab that we use in our classes, and I tried to dig into them. I figured I'd just Google on all these and find out what the output powers were. Guess what? That is not that easy to find. I would like to see the vendors of this equipment make it easier for us to determine antenna gain. Most of these devices will have unity gain, so you can kind of figure on that, but you can't be 100% sure. So I'd like to see the manufacturers publish that information. What is the maximum output power of these radios, and what is the gain of the antennas, so that we can more accurately site survey and design our networks. There's no reason for them to withhold this information. I'm sure they're not doing it intentionally. Probably think that there's probably just not a lot of interest, and there is interest. We need to know this information on the client devices. So look at this range of different devices, and this is just from the lab here. The Intel WS5300 is a 3x3 device. That is the only one that I've actually seen 150 megabits per second come on out of, is that particular Intel WS5300 internal mini PCIe chip. It was built into I think it was an HP laptop, and I just saw that a few months ago. Okay, I've got several Linksys 802.11n. I've got the USB and the PC card formats here, and USB. Actually, both of those are 2x3. It says here 2x3. I could have sworn that was a 2x2. I might have a typo here. Let me know if you have any different information or if you have questions on that. But I believe that's a typo. I think this Linksys WUSB 600N is 2x2. I know the Ubiquiti SR71 is 2x2, but that is has very high output power, so 24 dBm compared to 16 dBm. And many of the client devices that you'll be working with, which are legacy, maybe not 802.11n, may have much lower power levels than this, 15 dBm, 14 dBm, some even lower. So some of them may go down as low as 12 or 10 dBm maximum on the clients. So that's why it'd be nice to know that, so you know how to appropriately set your access points. But notice the number of spatial streams. I've got a brand new Acer Aspire 1. It's not a dual band, but it's a nice little laptop, but it's only a single stream in each direction. It's 802.11n. 150 megabit per second signaling rate is the transmit and receive phi rates on that. So as you can see, all different levels here, and it's kind of up to you to dig in and see what your equipment will support. But this is a big part of why your access points may support 300 megabits per second, and your client devices just may not be able to support that. Okay, so on 802.11n security, I just really have one thing I want to share with you, and that is this. With 802.11n, please use CCMP AES encryption only. If you try to use any of the legacy or previous versions, for instance, Temporal Key Integrity Protocol or TKIP, or even the now deprecated wired equivalent privacy WEP, if you use either one of those on your network, you will not get 802.11n speeds. If you design your network, site survey it, calculate your clients, do everything you need to do, build a perfect network, go out and site survey, prove that you've got 300 megabit per second signaling rate everywhere, and then go turn on TKIP encryption, you'll never get more than 54 megabits per second. Let me say that one more time. If you want to get speeds higher than the legacy rates of 54 megabits per second, the only 802.11 security cipher suite that will allow you to get 802.11n speeds is CCMP, which is a mode of advanced encryption standard. Okay, so do not use TKIP, do not use WEP, use only CCMP. It's as fast as not using anything at all. And we do not recommend that you do not use anything at all. Always use CCMP. Okay. All right then, and that brings me up to the section on channel usage. So with this, I would like to share with you an animation that I put together. Been working on this for a couple of years now, and this is the latest version of the Wireless Training Solutions Channel Simulator. And in class, we have all kinds of discussions. Everybody's got their own opinion on the channels. Most people know that the most popular 2.4 gigahertz channels, non-overlapping channels used not just in the US but in the world, are channels 1, 6, and 11. Okay, how that works is like this. So here we put together this animation, and it's actually a flash simulation, and with the channel simulator you can just click on these buttons to turn on the 20 megahertz channel masks that go with 802, all the versions of 802.11. These channel masks in the 2.4 also have the optional 22 megahertz ranges showing here. If you look at the channel mask, you'll see how it goes from -11 up to +11. Well, that means that on either side of the center frequency there's 11 megahertz of channel occupation. So when you turn on an 802.11b or earlier access point or client device and you set it for channel 1, then those devices will occupy 22 megahertz of spectrum, and it works that it's 11 megahertz on either side of the center frequency. Okay, so for instance, if you were to set an access point on channel 3, then channel 3 would occupy, when it's transmitting, it would occupy the space from approximately channel 1 all the way up through channel 5 when it's transmitting. And that's why we so carefully need to design our channelization and how the channels are used. Because if you have someone transmitting on channel 3 and someone transmitting on channel 1, that's probably going to result in a collision. And collisions really slow the network down a lot. We want to avoid them as best as possible. Okay, now if you don't believe in using channels 1, 6, and 11, I'm fine with that. You can figure this out with the channel simulator. You can prove to yourself any combination of anything you want to do You can turn on as many channels as you like and see how they work and how they fit and what they do. What I mostly want to look at is how 40 megahertz channels affect our 2.4 gigahertz spectrum. So here in the US, there are two 40 megahertz channels that have been specified. So you can either use the lower 40 megahertz of the 2.4 gigahertz spectrum in the US, or you can use the upper set. So if you were to turn on, but either case, you can only turn on one 40 megahertz channel in the US without causing collisions, so and interference. So because of that, there are very stringent rules built into 802.11n, especially on the 2.4 gigahertz band, that have to do with the use of 40 megahertz channels. So in the US, if you were to turn on the 40 megahertz channel that occupies bandwidth pretty much from channel 8 down through almost to the Wi-Fi limit, which is down below channel 1, then when you're transmitting, nobody else gets to talk in that whole set. So that would be everything from channel 1 and channel 6 and everything in between. You can, however, fit in a 20 megahertz channel up at channel 11. So you could use one 40 megahertz channel below and one 40 megahertz channel at the high end of the 2.4 gigahertz. The other option would be to turn on the upper 40 megahertz channel, which is pretty much centered on channel 8, and you would have room to put another 20 megahertz channel at the lower end. Okay, so now if you're fortunate enough to fall under European Telecommunication Standards Institute's rules, then you have a little bit more leeway. If you are on ETSI, if you're following the ETSI specifications, you can actually, because you've got all the way up to channel 13, you might be able to fit in two 40 megahertz channels. Now the way OFDM works, as you can see, these two 40 megahertz channels are touching on their edges. That's probably okay because of the guard subcarriers that are built into OFDM. So they probably, even though they are adjacent and are touching at their edge, because of the guard subcarriers and the way OFDM works, these two transmitters probably would not cause interference enough to result in a collision to each other. Okay, now quickly, if you want to see how the 5 gigahertz band breaks up, and we are running out of time, so I'm going to have to speed this up. But you can play with this. Scott Williams has made this available to everyone who attends the session today. He is sending out an email with the link so that you can go in and play with this as much as you want. And so let me just basically show you the 5 gigahertz band. With the 5 gigahertz band, you have much more frequency space, so you can turn on 20 megahertz channels here, like so. Now here's a best practice. Because of the way the 802.11h amendment specifies dynamic frequency selection for Uni 2 and Uni 2E bands, which are channel 52 all the way up through channel 140, those frequency ranges, we kind of suggest that you don't try to use those for real-time voice and video, anything that requires quality of service. And the reason why is because you can't statically select those, and it's possible that your equipment could sense radar in one of those channels and then move you off, and that dynamic frequency selection process can take a minute per channel change, and it can take quite a bit of time. Well, you don't really want that happening if you have access points that are trying to act as a foundation for roaming voice and video users. So we suggest that if you are putting your voice and video real-time services in the 5 gigahertz band, then use the Uni 1 and the Uni 3 static channel, or the Uni 1 and Uni 3 802.11 5 gigahertz channels, but assign them statically. So you can set channel 36, channel 40, 44, and 48. You can also use channels 149, 153, 157, and 161. So those channels you can assign statically, but the Uni2 and Uni2E you can't. You just select the range, and then the equipment has to decide which channel to use, and it may decide to move you at a very disadvantaged time. So this might be a better way to do it. Another advantage to doing this, because there's so many channels to work with in 802.11, what were previously the 802.11a channels, although that's a huge advantage for engineering large networks, it does require that when a roaming user moves from one channel, he has to scan a much larger channel set, and that can take a longer time. So by reducing the channels to just Uni 1 and Uni 3, now your users only have to scan through 8 channels rather than all 23 channels that they normally would have had to scan through. So that can make their roaming times a little quicker and more expedient. That doesn't mean that you should waste the DFS channels. These are perfect. This is the perfect playground for data, because data, it's not going to be too concerned if you move it out. If the equipment determines that it needs to move to another channel, that's not going to affect data as much as it's going to affect your real-time services. So you may decide to put all your data applications on Uni 2 and Uni 2E, and if you do, then that would be a good place to set up 40 megahertz channels. So you can use either 40s or 20s, you can set them up this way, or if you want, you can set up 40 megahertz channels and lots of them, and have lots and lots of capability. Look at all the 40 megahertz channels you could put on Uni 2E, and you still would have at 140, you can have a 20 megahertz channel, and at 165 another 20 megahertz channel just for data. So again, you can slice and dice that any way you want. You can make 108 and 112 20s, any combination you want. What's nice about the channel simulator is you can visually go in and plan and see what all the different ways that you can use these multitudes of channels. So I guess I better move on and let you go out and play with this yourself and see what you come up with. One little gotcha: when you go in and set this up the way I've created this simulator, if you click back on 2.4, then you wiped out anything you did. So you might want to take a screenshot if you get things set up nicely. But that also clears the channels for you. Okay. So remember, Scott Williams will be contacting you all through email to let you know how you can access the channel simulator at no cost. And have fun. Let me know of any suggestions you have for improving it, or if you notice anything not working right. I'm glad to hear that feedback from you and see if I can make it better for you. Okay. Now let's go quickly over a summary of best practices, and these are, generally speaking, best practices for 802.11n. Although the first one kind of goes, for everything. Overlap the cell edges. When you're designing your networks, you want to allow the cell edges to overlap by somewhere between 10 and 20%. Different applications will have different cell overlap coverages. If there's a lot of roaming going on, you probably want a larger cell overlap to give your equipment time enough to locate a new access point and be able to go through the roaming steps before your user actually leaves that first coverage area and enters the province of the second one. Okay, for 802.11n, always use only CCMP or AES, whichever way you prefer to call that, encryption. If you use anything else, you will only get the old legacy data rates, maximum of 54 megabits per second, even though everything else is looks like it should be supporting much higher rates. The encryption itself will not scale up past 54 megabits per second unless you use CCMP AES, and that's better anyway. I know that not everybody has upgraded all of their equipment to support CCMP, so if you must support TKIP, then you can't expect to get the full rates of 802.11n, so that should be in your design plans from the beginning. Then you would want to determine, either based on your your propagation studies or by recommendations from your vendors for the applications you're going to be running on your network, you'll need to determine either the proper received signal sensitivity threshold levels or the signal to noise ratio levels that you will use to determine the sizes of your cells and where they should where you want the cells to end so that you can match the overlap and coverage areas. And then you'll need to determine the best type of cell size that you want to use for these applications. So it isn't always best to just make the largest cells possible. High output power, the higher output powers that you can get up to the maximum output powers of your client devices would create the largest cells, and that allows you to have less roaming, but it also means that you'll be able to support fewer users. Okay, so the larger the cell, remember that you can only have one transmitter per cell. The bigger you make that cell, the larger of an area that you have to restrict to one user at a time. Okay, so the fewer users that you will have is based on the size of the cell. This also means that you'll have slower speeds. At the edges, the larger the cells are, the slower the speeds will be. The best way to use large cells is for latency sensitive applications. They don't need super high speed, but you do want to kind of restrict the roaming as much as possible. Now, if you have lots of users and they want the highest performance, then instead of large cells, you want small cells. And the first way that you can go about doing that is by dropping the power down as low as possible, making the cells as small as possible. That allows you to have reuse the frequencies over and over more often, and that's the best way to accommodate large numbers of users and give them the highest performance in your network. So you kind of have to decide, do we want large cells or small cells, and go from there. Once you've done that, then you need to match the access point transmission output power, and this is the output power from the antenna, not just from the radio itself, but we're talking about the EIRP. That's the energy coming off the antenna, measured right at the surface of the antenna. The equivalently isotropic radiated power, the EIRP, is what we're comparing here. You want to match the access point to the client device, and it should be no higher. Now, I'm not saying that you should just find the lowest client in your network. What I'm saying is, depending on what clients your most important clients that you have to support. So if you don't care about the handheld devices, but you do care about the SpectraLink phones, then it's the output powers of the SpectraLink phones that you would be engineering the network for, and then matching the power of the access point to be no higher than what's coming off, let's say, the SpectraLink phones. Okay. In the 5 gigahertz band, perfectly fine to use the 5 gigahertz band. It's great. It's the 5 gigahertz is the future of 802.11. Feel free to use that. But remember, if you use 5 gigahertz for latency sensitive applications, then we recommend you statically assign the channels, and in order to do that, you'll have to use Uni 1 and Uni 3 only, because the channels in Uni 2 and Uni 2E in many parts of the world, those must be assigned to be able to dynamically frequency select in case there is radar present in that band. Okay, so but that means that that's a good area for you to put data, because there's plenty of channels to go around, and it's a good area, lots and lots of bandwidth there for 40 megahertz channels. As a general rule, don't use 40 megahertz channels in the 2.4 gigahertz band. It may seem to you that it's a good idea, and you know what, you may even be allowed to turn on 40 megahertz channels on your access points, but don't be surprised if you go in and check it out a little bit later on, you find out, well, they're not actually operating because the equipment is restricting that. Even though it may allow you to turn on 40 megahertz channels, they may not actually be operational. So you'll need to check that too if you desire to use that. Okay, well, that was a lot of information, and that was a short hour. And I just want to thank you all for your attention and joining us here today. Hope to see you again real soon. And as always, feel free to contact me through email. Scott has given you my email address in his portion, and glad to hear from you. And with that, thanks again, and goodbye.